Hello there. We have done practical before about electrical circuits, which you can able to find, in our YouTube channel. There was a request that we do something about theory. So we're going to do questions related to electricity. That is for IGCSE level. So I'm using a past paper from that is 0625 Physics Cambridge 0625. I have a number of questions from different past papers. Our main aim today, we want to look at, as we're looking at the definition of potential difference, the definition of EMF, that is electromotive force, and also how they relate with electric current and the resistance. So we're going to look at them as we look at through this question. So this is a revision question. This is a revision session, having in mind that you've gone through the topic of current electricity and you're familiar with the definitions of these terms that I've mentioned. We're going to use them and I will be able to show you step by step how we can able to work them through. Should you have any question, please drop it in the comment. If you feel maybe there's a mistake that I made somewhere, please share it there with the rest. Let's look at this. This is a question that got, so you will be able to realize that for every question, I highlight where I got the question and even the number. So this is 0625, variant 42, February, March 2017, question number 9. So the end of the number there that is ending is the number question. So let's look at this one here. The figure 9.1 shows a graph of current against potential difference, PD, for a filament lamp. So we have the graph. On the y-axis, we have current, and PD, we have along the x-axis. So this is a current voltage characteristic graph. Question number 1, we are being asked, state what happens to the resistance of the filament of the lamp as the PD changes. State what happens in the resistance. Now, before I look at Roman 1, Roman 2, we need to understand here that resistance, mathematically or according to Ohm's law, is defined as potential difference per unit current. So that is how we define terms of the formula. But then right now we are putting a graph of current against potential difference. This means that I is given by V over R, and to make it better, this is I is equal to 1 over R V. Why am I doing that? So that you can able to differentiate that this is our Y, and that means this is M, and this is X for that matter. So we don't have Y-intercept from the graph, as you can able to see. So it therefore means that our gradient, so the gradient is equal to 1 over R. In other words, R is equal to 1 over the gradient. 1 over the gradient. My handwriting is not that good. Forgive me, that is why I'm talking as I write. All right. So now, from 0 to 1, if you can able to check 0 to 1, so that is, so 1, 2, 3, 4, 5. So 1 will be here, 1.0 is here. Now, we need to look at the nature of the graph at this particular point here. You can able to see clearly between 0 and 1, the graph is actually a straight line. So if the gradient is constant, that means 1 over R, which is the gradient, is also constant, and therefore the value of R is constant. So the value of resistance there is constant, or we can say it remains the same, or is the same throughout. But if you look at between 1 to 8, so between 1 to 8, you ask yourself, what is happening to the gradient? What is happening to the gradient? The gradient is decreasing. And how do we know that? Because you can able to see the line is becoming less steep. So when the graph is becoming less steep, it means the gradient is decreasing. And if the gradient is decreasing, as you can able to see from here, when gradient decrease, then we expect the resistance is supposed to be increasing. So the resistance increases between those points. And that is according to the relationship. All right. At normal brightness, the PD across the lamp is 8.0 volts. Calculate for normal brightness the resistance of the lamp. We have already stated that R is given by V over I. And because we have V, which is the potential difference, we need to look for I. And remember, we have been told to use the graph, or normally we need to use the graph because the information is there from question number 1. That means A, B, C, D, whatever follows, we should be able to use the graph unless we are told not to. All right, so we need to read the value of current when V is 8. So 8 is here. So we need to draw a line. We're not going to miss it out. And it's not that strong, but you need to use a ruler when you're drawing your line. So for now, it's just to help us. Good. So here is where we are. So on the y-axis, you see that we have, so each small box represents 0.02. 0.02. So that means here we have 0.62, 4, 6, 8, 10, that is 7, 0.72. So here is 0.72. So now the value here becomes 8.0 volts divided by 0.72 amps. We need to check on the y-axis, is it amps or amps? Yeah, the unit is in amps. That's correct. So 8 divided by. So this becomes 11.1 recurring into 2 significant figures, because I've used my values are in 2 significant figures. My value here will be 11. That is ohms, which is the unit of resistance. But Roman 2, we are asked to find the power of the lamp. So I have V, I have current, and I have resistance. I can use any. So power P is given by IV. So I will use here. So IV, so that is the current is 0.72 times P, which is 8. So that gives us 5.76 into 2 significant figures. We'll have 5.8, and that is watts. All right, so it extends. But in 5 of these lamps operating at normal brightness are connected in parallel to a power supply. So the power supply is there, but then now the normal operation. So for it to operate normally, we have been asked here, at a normal brightness, the PD is 8, and the current, we have realized it is 0.72. So we have almost everything. Find the EMF. So the EMF is the total potential difference in supplied by the battery or the power supply. So if there's a potential difference here, let's say V1. No. For this one here, because the lamps are connected in parallel, so when components are arranged in parallel, so if we have here V1, V2, V3, V4, V5, so the potential difference across them will be the same throughout. So V1 will be equal to V2, which is equal to V5, and which is equal to the EMF designed by capital E. So meaning that the EMF is equivalent to 8.0 volts. Find the total current, determine the current from the power supply. The current from the power supply, this is what happens here. So we have from the power supply, assume that this side is positive, then I will have here current I. Now this part of current here, part of it will flow here. because current splits, since there's a junction there, so total current I from the power supply is given by I1 plus I2 plus I3 plus I5. Now, these bulbs are identical. And if they're identical, then that means they have the same current. So there are 5 of them, 1, 2, 3, 4, 5. So we just take 0.72 times 5. That will be for here. So the total current, so the current will be 0.72 times 5. And that gives us 3.6 amps as the total current supplied from the power supply. Let's go to another question. Number 2, determine the electromotive force. Determine the electromotive force. Oh, define the electromotive force. How do we define electromotive force? As a circuit, so we define EMF as the energy transferred per unit charge. Energy transferred per unit charge by the battery or a cell to a charge, or in moving a charge in a circuit. So in other words, mathematically, we define this as energy, which is work done per unit charge. So this is work done or energy transferred by the battery to the charge so that the charge is able to move in a circuit. Number 3, the figure 7.1 shows a circuit diagram that includes component X. Component X. State the name of component X. You can be able to refer to the current IGCSE textbook so that you're able to learn the electrical symbol of all the components that you are required to know at this particular level. But if you see this component here, this is none other than a thermistor. This is none other than thermistor. The temperature of a thermistor is inversely proportional to the resistance, to its resistance. And we are talking about a thermistor here. We are talking about a special type of thermistor that is called NTC, that is negative temperature coefficient. Of course, at our level in IGCSE, we just need to know that it's called a thermistor, but then now should you do physics into higher level, then you realize you need to be specific. So the one we learn at IGCSE level is the negative temperature coefficient, whose resistance is inversely proportional to the temperature. You can even use theta. Let's look into this. The electromotive force EMF of the battery is E. The switch is closed. So the potential difference PD across the 30 ohm resistor is V30. Okay. So the PD across this, that is V30. The PD across the 20 ohm resistor is V20. So that is V20. The PD across the component X is Vx. Vx, correct. Now, in the equation, state the equation that relates Vx to V30. Vx to V30. Now, this component X, which is thermistor, is in parallel to the 30 ohm resistor. That means the potential difference across each of them is the same. So meaning that Vx should be equal to V30. Roman 2, E and V20. E and V20. So remember the combination of thermistor and the 30 ohm, that combination is in series with the 20 ohm resistor. That means if we have E here, then E is supposed to be total, so we'll have E is equal to Vx plus V20. Vx plus V20, because now the PD across X and the 30 ohm is Vx, which if we add it to V20, that should give us the total PD in the circuit, which is the EMF. And that is how we manage that particular part there. Question number 4. I forgot to include which paper that I got it. I'll be able to do that. The power supply used in an electric vehicle contains 990 rechargeable cells, each of electromotive force or EMF 1.2. The cells are contained in packs in which all the cells are in series with each other. The EMF of each pack is 54. Calculate the number of packs in the power supply. So this is not electricity, this is a logical question. So if we have all of them and we are going to pack them into that, so the first thing we need to do is to find that if we have 990, then what will be the total PD? So we will have, so 990 times 1.2, 990 times 1.2, that is if they're supposed to be in series, all of them, that will give us 1188 volts, the total. So that if we put them into packs, then now we have 1188 volts. We want to know the number of packs because each pack is 54. Then we divide by 54. That will give us 22. So the number of packs will be 22. So that is not electricity. That is a logical question, which involves also the knowledge of electricity. Now, part B, when in use, each pack supplies a current of 3.5 amps. Calculate the rate at which each cell is transferring chemical energy to electrical energy. So if we have been asked to find the rate at which each cell is transferring chemical energy to electrical, the rate, that is actually power. That is power, and power is IV. That is power, which is IV. So we have been given up here. We have been told that each have a EMF of 1.5 volts. So that is for each cell. But then now, because if it supplies a current of 3.5, and remember those cells are in series, that means that for each cell, the current flowing through them will be, or the current that they are producing will be 3.5 because they're in series. So we'll have 3.5 times 1.2. 3.5 times 1.2, which is 4.2 joules per second. So the rate of energy, so that is joules per second or watts. Now, the packs are connected in parallel to supply a large current to drive the electric vehicle. Explain why it is necessary to use thick wires to carry this current. So what you know is that for thick wires, R is inversely proportional to the cross-sectional area. What does it mean? It means that for thick wires have less resistance. And when there's less resistance, that means there will be less heating effect. So that means there will be less heating effect on the wire, or in other words, there will be less thermal energy generated in the wires. So what is the advantage of this? The advantage of this is that this reduces the risk of the wire melting, even the insulator. The wire, the insulator the insulator melting. It can even go to an extent of even causing, minimizing the fire that may arise due to the heating effect. So that is done. So let's look at the next question. So remember, we are trying to understand what EMF and PD, is. And when you look at this circuit, they help us do that. So number 5, define EMF. We have already done this. We have already defined what EMF is. So EMF, we are looking at the work done by the cell or battery on the charge, and that is per unit charge. But I don't know whether we have PD here, but if you're looking at PD, so PD is work done now by the charge on a given component. That is per unit charge. Anyway, let's continue. So part B, figure 7.1 shows a circuit. So we have this, we have, okay, 2 lamps shown are identical. Each lamp has a potential difference of 3.0 volts across it and a current of 2.0 amps in it. PQ is the length of wire. The resistance PQ is R. Calculate R. We need to understand if there is a current flowing which is 2.0, there's a current here flowing which is 2.0 amps. That means the current into the junction is the addition. That means the current into the junction is supposed to be 4 amps. And therefore the current flowing through this wire here is 4.0 amps. Again, if the PD is 3.0, so here PD is 3.0 volts, here also 3.0 volts because they are in parallel. So the PD across them is just 3.0, which is in series with this. So if we call this V, then that V will be, so that will be 12 minus 3, which is, that is 9.0 volts. So to find R is V over I. R is V over I, and therefore there is a 9.0 V over current, and current is 4.0 amps. So that is 9 divided by 4. We get 2.25 into 2 significant figures, 2.3 ohms. Remember to be aware of the number of significant figures as you're doing your calculations. Roman 2, another piece of wire is made of the same metal as PQ. The length of the new piece of wire is twice the length of PQ. Okay. The diameter of the piece of wire is twice the diameter of PQ. So let's use the ratio here. So R is directly proportional to the length and inversely proportional to A. So the first R, let's say, is given by this. So we call this one R1. Now for R2, we are being told that now the length of the new piece of the wire is twice. That will be now 2L. And then the diameter, diameter A, because you're going to assume that is circular. So diameter, that will be like pi R squared. So that will be pi D squared over 4. Pi D squared over 4. So let me rewrite now. R1 is directly proportional because pi and 4, they are constants. So that means R1 is directly proportional to L and inversely proportional to D squared. Yeah, so that is the right one. So for R2, L is twice, so 2, that is 2L, and then diameter is also twice. Okay, so we'll have now 2D, but is squared, so that will be 2L over 4D squared. So that is like a half. So remember, L over D squared is the R1. So R2 is basically equal to a half of R1, and that is a half of 2.3. So a half of 2.3, that is, we expect 1.15 into two significant figures, 1.2 ohms. All right. The next question, that is 4-1 October, November 2016, number 8. A battery is made up of 8 cells in series. Each cell has an EMF of 1.5. Calculate the EMF. So if they are connected in series, that means what we're doing is just to add the EMF to give us the total EMF of the battery, because so cells make a battery. So just take 8 times 1.5. If they were in parallel, then the EMF could just be 1.5. If they were in parallel. So that gives us 12. So EMF is 12, and that is 12 volts. Calculate the energy transferred from the battery in 40 minutes. 40 minutes. So sometimes students always forget whether we need a question to do with is it power, is it energy, and then you keep on wondering, how do I know the formula for energy? How do you master them? Please just know the definition of one. If you cannot know the definition of power as the rate of doing work, so power is work done per unit time, then you should know that work done is power times time. Just this formula can save you a lot. So, and then power, we know it is IV. So you deal with what you have. And if I look at this question here, the battery connected the, a resistor. So for us to know the energy transferred from the battery, so we have the output that. So from here, work done or the energy is given by power times time, and power is IV, so that is IVT. And then we don't have current. I don't want to calculate it, but I know that current is V over R. That means the work done or the energy transferred is V over R times this V, that becomes V squared times T, and T must be in seconds. So we will have V as 12 squared over R, which is 8, times the time, which is 40 minutes. That 40 minutes must be converted into seconds, so you multiply by 60. Instead of using dot, we just use multiplication here to avoid confusion. So that will be 40 times 60 times 12 squared. We divide everything by 8, and that gives us 43,200 joules, which you can just write as 43,000 joules into two significant figures. Describe the energy changes that take place during the 40 minutes. So during the 40 minutes, we have the battery that is supplying. So that is changes from chemical energy, because there is a wire, for that there must be a circuit. It is connected to a ohm resistor. So chemical to electrical energy. Electrical energy across the resistor will be converted to thermal energy. All right. We have our last question here, which is, so definition of electromotive force. Remember that is 2 marks, so please, when you're defining this term of electromotive force, you talk about energy transferred per unit charge or work done per unit charge, by a battery. You mentioned about a charge moving in so there must be. So this question number 7, this is our last question. So part B, an electric heater contains 2 heating elements, that is R1 and R2, as you can able to see on the diagram. An electric motor operates a fan. The fan blows cool air over the heating element. Okay. So the heater is powered by main supply of EMF 240 volts, which you can able to see. Switches S1 and S2 are closed. Heating element R1 gets hot. The resistance of R1 is 30. Calculate the current flowing through R1. So remember, if they are all connected, so switches 1, all of them are closed, you can able to see clearly that R1, R2, we have only closed S1 and S2. Okay, so S1 and S2 are closed. So motor R1 and the main supply, they're in parallel. That means so I is V over R. So that is 240 volts because it's parallel. So parallel, the EMF, the potential difference is the same. So that is 240 divided by 30. You divide, that will give you 8.0 amps. Remember, this value here will give you 8, but our answer is supposed to be into 2 significant figure. So we have 8.0. Calculate the power produced in the heating element R1. So power is IV. So that is 8 times 240. So 8 times 240, you get 1920 watts. Can be 1900. The resistance of heating element R2 is 60. Switches S1, S2, S3 are closed. Student explain how the current in R2 compares with the current in R1. So if all of them are closed, of course, you look at the resistance. So the resistance of R2 is higher, is greater than the resistance of R1. And since current and so from Ohm's law, IR, for the same potential difference, I is inversely proportional to R, meaning that the current, because R2 has a greater resistance, that means the current in R2 is less compared to the current in R1, and that is because of this. Remember, there are simple equations in this. So always remember, from Ohm's law, V is IR. Not forgetting from electric charge, that charge is given by IT, where T must be in seconds. Power is given by IR. Power is given by work done per unit time, meaning that work done or energy transferred is given by power times time. But because power is IR, so we have power is IV. So IV, so we have IVT. If we master this, it will help us. Manipulation of this equation depends on this. Because, for example, if I want to calculate power and I don't have current, then I know that current I is V over R. So I will just put it there. So where there's I will put V over R multiplied by this V, and that will give me V squared over R. We don't need to master all this. As long as we have the main one, we can always manipulate the equations the way we need. So guys, see you in our next video. And please, you know what to do. Subscribe to support us, to give Mwalimu Ndolo, motivation to produce more videos to help you pass physics. Thank you. See you guys.